And we are live. Hello, everyone.
We are live.
Oh,
Hi.
I can see it. Okay, cool. Okay, hello, everyone. You can see as well known faces. OX, Efrain. Nice to see you here. Um, yeah, welcome, Lucas. For this first workshops on Madara. I think that lots of people are eager to learn more about Madara and how as well to participate in that bounty. I think like many people already in the chat I saw many questions as well on Madara, and so lots of people reacting on Twitter on Madara. So so that's really cool. So yeah, so this first workshop on Madara will be diving into the Starknet Stack Madara, and I'll give you the word to the known Lucas from Starkware.
Thanks. Hi, everyone. So today, as Edouard said, we're going to speak about Madara, which is a Starknet sequencer based on Substrate. So we're going to dive in the code and see how everything from Starknet is coded in Madara. So let me share my beautiful slides. Here. Here they are. So what we're going to do is go in the doc and check what concept we have and see how we implemented that in Substrate. So first thing is account abstraction, which is a big topic. So for those who don't know, in Starknet, there's no EOA like in Ethereum. In Ethereum, you have a private key that controls a public key, and you need to sign everything in order to send a transaction. In Starknet, everything is a smart contract, even accounts, and you can define whatever logic you want. So uh, let's see how it's handled. So in Substrate, you have two things, the runtime and the client. The client is what handles the communication between the nodes and everything in the outside world. And the runtime is everything that has to be deterministic. So all the state transition function. So all the execution of transactions and everything happen in the runtime. In the runtime, we can have what's called extrinsics, which are entry points that execute logic. So in Starknet, we have um, multiple transactions. We have three transaction types: invoke, declare, and deploy. And in Madara, we defined three extrinsics: invoke, uh, declare, and deploy. So what you can do is use the Polka.sdk to send an extrinsic, which is a transaction, or you can use Starknet.js to send it through the RPC, which we'll go over later, and that will submit your transaction. So for transaction validation, there are two types of extrinsics, signed and unsigned, and we use unsigned. So we need to define our own validation logic. So otherwise, you could just spam the with invalid transactions, and your node would be overloaded. So we need to define something to say, okay, this is a transaction sent to this smart contract. It's valid, it's intended, and if the execution reverts, then it's something else. But we need to have something similar to signature verification. Uh, so in Substrate, there is a macro that will do that for you. So just define this function, you implement this trait, and you implement the logic you want. So if we have an invoke, we want to validate the invoke. Same thing for declare and deploy. And so this will basically just run the validate entry point of a smart contract, because smart contracts account contracts need to define uh, like to implement a certain API, which is here. So you need validate, declare, validate, and validate deploy. And we'll just run this entry points in the validate unsigned, this one if it's a declared transaction, and this one if it's a deployed transaction. So this is how it goes for the validation of a transaction and the account contract. Then what we have there, validate execute. Okay, we have that. Contract classes, yes. So in the runtime, we can have palettes. Here we define the Starknet palettes, and we have all the Starknet logic. So we have the storage, we have the configuration, we have the transaction types, we have a bunch of things. And here we have all our storage variables. So here is all that is stored. So here we have the pending events. We have the current block, a map from substrate block hash to Starknet block hash. Here contract class hashes. So a mapping from contract address to contract class. And here a mapping from contract class hashes to contract class. So whenever you send a transaction, we need to load the contract class. So what we'll do is we'll check the address you're sending a transaction to, and then we'll go in, we'll use this mapping to get the class hash corresponding to the address. And then this, from this class hash, we'll get the class, the contract class, and load the contract. We're not doing this at Madara level. We're using the blockifier, and the blockifier we need to implement a trait, a specific trait, to read and write in the substrate storage. So we implemented that here. So here is the trait to read the storage, and here is to write the storage. So basically, what we're doing when we're executing a transaction. We're going here. We're getting the block context, which contains the block number, the block timestamp. Those are useful for the syscall get block number, get block timestamp. We get the fee token address in order to charge for fees, the chain ID to compute transaction hash and everything, the sequencer address to transfer the fees to the right address. These are this is to compute the fees. These are the max steps allowed per transaction, and this is the gas price. So for now, the gas price is hard-coded, but there's an ongoing PR to use the gas for bill 1. So it should be merged soon. And then return the block context. Okay, so we have the block context. We now have to convert the external transaction type to the internal one. So this is what's allowed in an invoke transaction, and we just convert it to the right type. Then we execute it. In the execution, we're verifying the transaction version because, as you know, Starknet defines a ton of transaction version because of upgrades. So we need to verify this. Then we need to get the account context, which is that. So the transaction hash, the max fee, the version, the signature, the nonce, and the sender address, which is the account address. Then also we execute that. Then what we're doing is we're checking for the nonce. So if the transaction is an invoke version 0, we had nonce abstraction which wasn't enforced in the protocol, so we're not checking the nonce. If we have a transaction 1 or 2, whatever, we check that the current nonce is the expected nonce. Otherwise, the transaction is invalid. And that's, yeah, otherwise the transaction is invalid and it will revert. Then we validate the transaction. We need to rerun that because it will be counted in the fee transfer. We charge for this. So we run it. Then we run the executes entry point, which is somewhere, whatever, which is here. So we run that. We run that here with all the information, and we wrap the blockifier logic. So this function is from the blockifier. Yeah, this function is from the blockifier. So in Madara, we have like we're doing like the bridging between the RPC and the blockifier. So yeah, here we verify, we execute the transfer, we verify that everything is correct, and then we charge for fees somewhere. Yeah, here. Uh, blah, blah, blah. Yeah, we charge for fees in the execute. Yeah, we charge the fees here. We redefined all the functions because the runtime, the substrate runtime has to be wasn't compatible, so no STD compatible, and the blockifier uh, is not no STD compatible. So we had to we're using a fork, but for some functions it's too hard, so we just redefine them with the right types. So we have all the fee logic here, and then we just return the transaction information, and we append that in the pending storage var, which is the equivalent of the pending block in Starknet, but it's not really useful for the outside world. So yeah, this is the palette, and the palette needs also have an interesting functionality, which is the off-chain worker. So the off-chain worker is in the runtime and is triggered almost at every block. I say almost because it said in the documentation that we shouldn't rely on the off-chain worker if we need something to be triggered at every block. So maybe at some block it's not triggered, but whatever. We're using that because we need to access the L1 data to get the messages from the Starknet core contract. In Starknet, here, L1 L2 messaging. We can send messages from L1 to L2, and it's right there. So what's happening is that on L1, you send a message to L2 by sending a message in the Starknet core contract. And then after 10 blocks, we'll pick up that message and we'll execute it in Starknet. So we have this wrapper function where we get the last known ETH block. So if for some reason we missed some blocks, we always get from we'll always start from the last known block. So we get the last known block, then we query the last finalized block, which is the last finalized block on Ethereum, and then we get all the events between this block and the latest block, and we scan them, we store them, and we try to consume them for every message. And if there's an error, then the transaction reverse, but that's not a problem. So this is for the off-chain worker, and it's really powerful because we can we can interact with the outside word from the palette. So it's really useful. And we're probably going to use that also for gas price. So yeah, that's something very powerful. Uh, Something else. Yeah, events. Uh, there are the substrate-based events, which are somewhere. It's in enum somewhere. And oh yeah, you basically define them as you would do that with that way. Oh, whatever. We have our Starknet event, which is there. So it has the keys and the data because that's how they're defined. So the keys is the Ethereum topics, and the data is the data you want to send. So I think we should have it here. Yes. So here is an event. So this would be the key, and all these would be the data. Uh, for now, this high-level syntax only supports one key, but in reality, you can have multiple keys. This will be supported in Cargo 1, and this is why we have multiple, like an array of keys and an array of data. We need also to use, yeah, one thing is that as it's a blockchain, we don't want the runtime to be stoppable. Otherwise, your blockchain crashes and your Solana. So we don't want that. So in order to have to avoid that, we need to bound everything. So we have to use substrate types that are bounded. So bounded VEC, bounded Bitmaps, bounded whatever. And this will prevent from getting dust by having infinite data that is being sent to your blockchain. Um, yeah, that's it for events. Data availability. That's a really interesting topic. So Starknet is a validity rollup, so we need to prove everything that's happening in there. So we need to integrate with a prover. Of course, we'll integrate with Sharp, but we need to integrate the API and design everything. So this will happen in the client somewhere in a specific folder. Ben is working on that and we'll talk about that. But what you need to remember is that we'll basically have a service that will send all the traces and format the job to send it to Sharp so that we'll be able to prove what's happening. And we'll also have a service for data availability. So you can send your data to Ethereum, you can send it to Celestia, to whatever the solution you want. Um, yeah, that's it. Starknet state. So we do not have that currently. So the Starknet state is a Merkle-Patricia tree of Merkle-Patricia tree. Each contract is a Merkle-Patricia tree with its storage vars. And the Starknet root is composed of the root of each contract is like a node in the Merkle Patricia tree, and then you get the Starknet root. But we don't have that yet, and this is something we fear will like destroy the performances of Madara because it's a really heavy computation, and there are lots of hashes that are implied, and the Peterson hash is really slow. So we're afraid to do that, and we're delaying the day we're doing it. Right, for the runtime, I think that should be it. Yeah, no, small thing. So substrate has basic components. So it has block, transactions, all those things. And they're not the same as Starknet blocks. So we have to create a wrapper block that will have all the Starknet useful information. So in the primitives, in the block, we have the block header. So this is the block header that we have, block structure. Here, so you see you have all those fields. We have them here. And in the hooks, in the unfinalized hook, when we store the block, we store a Starknet block. The substrate block is automatically saved, and we wrap the substrate block in the structure here, and we save it. So in the RPC we can return like the right information and not only the substrate information. Yeah, these are hooks. Forgot to mention, but those familiar with uh, um, React should probably know what are hooks, but whatever. This onFinalize is triggered every time we finalize a block. This function is called, and what we're doing is we're storing the Starknet block. Uninitialize, when we open a block, this is called, and for now we're doing nothing, but we might be doing something. On runtime upgrade is when you upgrade the runtime. So Substrate has a really powerful mechanism, which is forkless upgrade. You can upgrade your runtime. So this is why it has to be compilable to WASM. You're sending the runtime in the blockchain, and every node will upgrade its own runtime, and you won't have a hard fork. So this is really powerful, and uh, that's why we need to maintain the no STD compatibility. Now, in the RPC, because we need to be compatible with the Starknet tooling, we're defining the Starknet RPC. So we define a trait with all the methods that we want. So these are from the specs, and then we implement them here with the logic. So we'll go through um, get block member, I think, and maybe it doesn't exist. We don't want that. Oh, wait. Let's go through this one. Get storage at. So this endpoint will return the storage of a contract, the value of a storage key in a smart contract. So as I said, Substrate has its own components. So we need to convert the Substrate block hash, the Starknet block hash into a Substrate block hash in order to retrieve uh, to retrieve like to be able to query the right state, because as in Starknet and Substrate, you can query the state at a certain block hash. So we need to convert the Starknet block hash into a Substrate block hash to query the state at the right block. So that's what we're doing here. And then from the the Substrate block hash, we're querying the storage key at this block hash. So yeah, it's defined there in the client. But what it's gonna do essentially is gonna go in there and go in this storage view and query the value, this value at the specified block hash. So yeah, this is what's happening in the RPC. For now, we almost have everything that works. I think only the declare broken because we are not computing the right class hash. So the signature fails and it's broken, but it should be fixed. It should be fixed at some point. Um, yeah. Going back to the state root, because it's a really important functionality because we want to be Lifeline compatible and they need the state root. So we need that crypto commitment. So for now, in this commitment file, we're committing on the events and on the transactions because here we have transaction commitment and event commitment. So what is a commitment? We create a Merkle tree of events and of transactions, and then we get the Merkle root and we add it in the block header. We should do that also for the Starknet state root, but as I said, we're not doing this yet. Maybe it's a good hackathon subject. Maybe not, I don't know. But that's probably where it should be done, uh, if you want to do that. Yeah, also in the runtime. So if you create a palette, so here we created the Starknet palette here. In the runtime, we need to instantiate it because there is a config here. We need to instantiate all those types. And this is also where we want to improve things because we want the Starknet palette to be highly customizable. So we need to be able to feed all the values from the runtime. So for example, uh, we have the transaction longevity. So if I go back in the unsigned transaction, back in the validate unsigned, we see that when we craft a transaction, we set its priority. So right now we're setting the priority. So the lowest nonce goes first. Otherwise, we get a bunch of nonce errors, and it's annoying. So this is the priority we set for now, but this should be changed at some point to when we have a real fee market and all this. And then we have to provide a longevity. So the longevity is if after the number input here blocks the transaction is not processed, then it's considered invalid. So we want this to be customizable. We want the number of steps per transaction to be customizable. So we saw that it was hard coded. Max here you see that it's hard coded. We want this to be configurable. We want basically everything to be customizable, to be able to create like app chains the best we can. This is where the events are defined. I don't find them, but it's here. So here we create the Starknet events, um, which is wrapping a substrate event. And I see that we're running out of time. If you guys have any question, I don't know if my chat bugged or if there's no question.
Yeah, no, there's no question so far. And as well, Luca, thanks a lot. If you want to continue, we are not stuck with the time. I just like put 30 minutes, but we can obviously go way more time as well. If you still have things to do, don't be don't be stuck with the time and push with the time.
Okay. Yeah, I'll go over the tests, I think, because they're really important also. And yeah, I won't last too long because it must be quite boring. So we have unit tests in Rust to test all the components of the runtime. So we need to remember that this is a blockchain, so it has to be super secure and super tested. So we're testing all the everything that we're doing. We're testing it. So these are the unit tests of the palette. In the primitives, we also have tests. Well, we should have tests. Yeah, we have tests. We're testing that. And we also have end-to-end testing tests there. And for that, we're using the Starknet.js. So it's the JavaScript SDK. And we're testing all this. There are lots of tests, but we need to improve them to be extra sure that we're not breaking anything or that we don't have a security breach. But this could and should be improved. Um, yeah, so and to run them, so yeah, maybe I should explain how to run the project. So you'll need to install Rust. I think you can just run Rust app show, or yeah, no, when you, so we have a Rust toolchain file here. So when you'll compile the project, it will install the right toolchain. But so if you want to compile the whole project, you will need a bunch of dependencies. The README here. You can scroll and you'll find the dependencies. Then, if you want to build the whole project, you can run cargo build. If you you should cargo build only when you want to develop and to rebuild fast, so you can uh, so you can build faster. Otherwise, if you want to benchmark it, you can cargo build release. Um, this build will be longer, but you'll have more performances. So that's why you should uh, build that if you want to benchmark it. Also, if you want to run a specific test or the test for a specific palette. So for example, you want to run the test for the Starknet palette. So you go there, you get that name, and you run cargo test dash p palette Starknet, and this will run the tests for the palette. If you want to run a specific test in the palette, for example, you run either that cargo test dash p palette Starknet, and then the name of the test, and it will run only this specific test. Then, if you want to run the end-to-end test, so you need to go there. You need Node version 20 at least, and you need to install the dependencies. Then you need to either build Madara in release mode, or you need to set some environment variable, which I can't remember. What it is. It's in the CI, so I'm gonna check there. Test and work binary path. Yeah, you need to set the binary path if you want to use debug mode. And then you need to run test sec, and it will run the test. So here they should all go through. Yeah. No. And if you want to understand why this fails, for example, you add Madara log info, for example, and then npm run test. and you will have the Madara logs here, and we'll see why it failed. So yeah, it's pretty verbose, but you can combine that with the only and then run the test, and you'll have your specific test that will be run in the TypeScript test. And here, yeah, you see, I only have one test that's sent. Beja asking, could you explain a little bit more about the runtime client primitives being STD compatible? Yes. So two components, client that's responsible for all the outside world communication, consensus, all those stuff, and runtime, which is the state transition function that has to be completely deterministic. So we need the runtime to be NoSTD compatible because we want every node to be able to reproduce the exact same thing. If we had STD compatibility, someone could throw a random number here. So you could use RNG, the RNG create, and create a random number and use it somewhere. And it wouldn't be reproducible by every node because it uses the entropy of your machine, and this would break the chain, basically. Also, for the forkless upgrade, we need to compile to WASM so we can propagate the binary on the network and upgrade every runtime. For the client, it can be STD. It can use the standard library because it's responsible for communication, and it's not what's done in the client doesn't have to be reproduced by every node. So it could have different client implementation. We don't really care. So that's why it doesn't have to be STD compatible. No STD compatible. Does that answer your question? Yes. Let's say that yes. Um, all right. Yeah, I think I'm done for this. Maybe if there are some questions, I can answer them. Otherwise, you should be good to read the code and understand it. Yeah, I'll just do a small summary. So you get into Madara, you build whatever you want, and then client is for all RPC. That's the only thing that you need to modify. The palette, if you want to modify the core logic of Starknet, and the primitives, we're using those primitives in the palette. So there might need some things to be done there, and they have to be NoSTD compatible. But yeah, I think I'm done for that.
Perfect. Nice. Really comprehensive and explanation and good workshops on the first walk into Madara experience in Madara world. I don't think we have any more question, or just shout it out now. But otherwise, Luca is as well one of our mentors, so there will be as well like a small description about him, and as well like giving the opportunity to send message to him through the TakeI platform, and also I'll share his Twitter and Telegram handle as well, and the description of the video that will be found on YouTube. So yeah, thanks a lot for this amazing workshop, Luca. I think it helped a lot of people to start with Madara.
Thank you for inviting me. And see you later, I guess.
Yeah, see you later, and yeah, let's continue to hack.
Yeah. Bye.
Bye bye.